Alright, section 1.4, intermediate value theorem. Actually a pretty intuitive idea. It says that we have f of a not equal to f of b, but they exist, okay, on a closed interval ab. So it does make sense to talk about f of a and f of b on this closed interval. They make sense, and f of x continuous on AB, and of course as soon as I say f of x is continuous on this closed interval AB, those two values here better exist, because otherwise I couldn't talk about the continuity. And so if we have that, then the intermediate value theorem says essentially that, okay, here's A, here's B, there's maybe f at A and f at B, they're not equal. Well, if it's continuous, then sort of no matter what it does, it hits every value in between, and so what that says is if I'm here at C, then what I can do is if f of, and now I'm just going to assume f of a is the bigger one in this case, okay, and but if it were the smaller one, we could still do the same thing. So if f of a is greater than k, but that's greater than f of b, then f of c equal k exists with a less than c less than b. Okay, we can hit every value in between those two things. And so we need the continuity, right? That's in this thing, and we need a closed interval, it says. Okay, so what could go wrong if we don't have those? Well, okay, start with the continuity. That's pretty simple. Here's A, here's B. I'll even, it doesn't really matter exactly where I put C, but for this value of K, no C exists. Right? There's, that's in between f at A and f at B, and yet there is no value for C for which f of x equals K. So we need the continuity, because if I don't have it, I can screw it up just fine. And then now, what about closed versus open intervals? Okay, so we know the function is continuous on the open interval, AB, and we need A and B, f of A and f of B to exist, or we could say they don't necessarily exist, but just consider something where we start here, and now in this case, just because of the way I drew it, we'll have f of A be small. Well, no, it doesn't have to be. Okay, so we've got this asymptote going up here, but then I go ahead here and put in a dot for f of b, right? F of b is at that height. And now it's still discontinuous, I guess you could say, is the problem, but we've got this open interval issue, and we could have an asymptote, and again, k might be in there somewhere. Okay, and if I'm a little fancier, I could probably think of I didn't spend time thinking about what's another example. Maybe I can come up with another example that uses the open interval part, but we still can't reach k. But, anyway, though, so no c exists. So we could have an open interval issue or a discontinuity issue, something like that, and but the point, I guess the point here is we still have a discontinuity in the function, but not in the open interval. So you see f of x is continuous in the open interval. It's just not continuous on the closed interval. And so you do need closed interval and continuity on the whole thing. Okay, so that's the intermediate value theorem. Now, typically, a big use of this, application, finding zeros. All right, because if if this is at A and this is at B, and there's my function f of x, then C, what I know is that f of x equals 0 for some C in A less than C less than B. Okay, so A was negative, or f of A was negative. All right, so here we had f of A negative, less than 0. Up here we've got f of B is greater than 0. And so f of x had to be 0 somewhere in between. And so if I'm trying to find places where a function is 0, once I get these two different signs for the function, I know to look somewhere in between. Now, it could be there's more than one 0, but there's at least one 0. So that's a typical application of the intermediate value theorem. Okay, we'll call that good.